plus 1 cube y equals x plus 1 squared times e to the power of x minus 3x cosine x. We can rewrite this equation as y to the third prime minus 3y second prime plus 3y prime minus y equals to x plus 1 squared e to the power of x minus 3x cosine x. As we can see here, we can now get our m. So we have m minus 1 cube is equals to 0. So we have our m1 equals to m2 equals to m3, which is equal to 1. So we can now get our y complementary. So we have yc is equals to c1 e to the power of x plus c2 x e to the power of x plus c3 x squared e to the power of x. And now using the process of undetermined coefficients, we get the y particular. So our first, since we have this equation x plus 1 squared e to the power of x, we have two terms in our right hand side. So we get from here, we get our y particular, which is in the form yp. We have yp1 for x plus 1 squared times e to the power of x. So our yp1 here is for that term is x cubed times a e to the power of x plus b x e to the power of x plus c x squared e to the power of x. Since we can write this as e to the power of x squared plus 2x e to the power of x and plus e to the power of x. So we have this a, where a and b and c are constant. Then after we get our yp1, we have our yp2 for our 3x for the term 3x cosine x. So we have yp2 is equal to d cosine x plus e x cosine x plus f sine x plus gx sine x. And these are now the equations of our y particular. So our overall y particular is, so we have yp equals yp1 plus yp2. Now we have our yp is equal to a e to the power of x cubed plus b e to the power of x to the fourth plus c e to the power of x to the fifth plus d cosine x plus e x cosine x plus f sine x plus g x sine x. Then after that, we can now get the first derivative, second derivative, and third derivative of yp, which we will substitute to our original equation later. So we have our y prime p, which is equal to right now I am getting the first derivative for yp. And the derivative of ryp is this. This is the first derivative of yp. Then now we get the second derivative of yp. I factor out the constant here so that it would be easier for us to manipulate the equation. And this is the second derivative of our equation. Now for the third derivative of yp, we get, this is our final answer for the third derivative. Just get the third derivative of it. I suppose that you know already how to differentiate, so I am not explaining any further about getting the derivatives of our equation. For the terms with b, actually our solution is, it is easy. What took us so long is we have a very very long solution. We have a very long time in getting the derivative because it's too long. And I suggest that you should be careful in getting your derivatives. No, I should. And this is now our third derivative. After getting the first derivative, second derivative, and third derivative, we substitute it to our original equation, which is y, third derivative of y, minus 3 times second derivative of y, plus 3 times first derivative of y, minus y, equals to x plus 1 squared e to the power of x minus 3x cosine x. Writing this, we get this. And on our right hand side, we have e to the power of x squared plus 2 e to the power of x plus e to the power of x minus 3x cosine x. And you see we have this third derivative, so we will substitute the third derivative of yp here, and for the second derivative, substitute the second derivative of yp, and for the first derivative, substitute the first derivative of yp, and for the y, we have our y, the equation of our y particular a while ago, and substitute it in this equation. In this step, we have to undergo this step in order to get the constants we have, which is a, b, c, d, e, f, and g. Substituting the value of the value of first derivative, second derivative, third derivative to our equation, we have this. This here, the terms here up to here is for our is the equation of our third derivative, y prime, and here we have 3 times second derivative of p, which is this. Just substitute it, the values that we get a while ago, and this is for our first derivative. We multiply it by 3 as what the original equation tells us, and we get this. And this is our first derivative. Multiply it with negative since we have minus. No, this is our yp, I mean, equals to, then equate it to our f of x, which is e to the power of x plus e to the power of x squared plus 2e to the power of x minus 3x cosine x. So we have this. Simplifying further after substitution, we get this. 6a e to the power of x plus 24b e to the power of x plus 60c e to the power of x squared plus 2d, quantity 2d plus 2f minus 2g times cosine x plus quantity 2e plus 2g times x cosine x plus minus 2d plus 6e plus 2f sine x plus quantity negative 2e plus 2g times x sine x, which is equal to e to the power of x plus 2e to the power of x plus e to the power of x squared minus 3x cosine x. Then from this we can now get the values of a, b, c, d, e, f, and g. So to get the values of the constant, first for a we have the term containing the a is 6a e to the power of x, and since in the right hand side of our equation we have e to the power of x, so we have e to the power of x. We have e to the power of x in the right hand side equation, so we have 6a is equals to 1 and a is equal to 1/6. That is for our a, and for our b we have the term 24b ex x, and in the right hand side equation we have the term 2e to the power of x. So we have now 24b is equal to 2. Then getting b, we have b equals to 1 over 12. Then for our c, we have the term 60 c e to the power of x squared, and in our right hand side we have e to the power of x squared, so we have 60 c is equal to 1, so c is equals to 1 over 60. So for our next term we have this 2d plus 2f minus 6g cosine x. Since our cosine x is 0, we have no term such which contains cosine x, so we can write our 2d plus 2f minus 6g is equals to 0. And for the next term, which is 2e plus 2gx cosine x, since we have here negative 3x cosine x, so we have 2e plus 2g equals to negative 3. So we have 2e plus 2g equals to negative 3. And for this next term, negative 2d plus 6e plus 2f sine x, we have no term which contains sine x, so we have negative 2d plus 6e plus 2f equals to 0. And here, and the last term, which is negative 2e plus 2g x sine x, we have no term which contains x sine x, so we have negative 2e plus 2g is equals to 0. So from this equation, we can get the value of e and g. So we have negative 2e is equals to negative 2g. So e is equals to g. And using this to here, we have now the equation 2e plus 2e, since g is equals to e, equals to negative 3, so we get e is equals to negative 3/4. And since e is equals to g, so we also have g equals to negative 3/4. Now, using this equation, 2d plus 2f minus 6g, and this negative 2d plus 6e plus 2f equals 0, so we have 2d plus 2f minus 6g is equals to 0, and negative 2d plus 2f plus 6e is equals to 0. So we can cancel this out. And here, since g is equals to e, we can also cancel this. So we have 4f is equals to 0, and f is equals to 0. Then substituting the value of f and e in this equation, so we have negative 2d plus 6e plus 2f is equals to 0. Since this is equals to 0 and this is negative 3/4, so we have negative 2d equals to plus 6 times negative 3/4 equals 0. Since f is equals to 0, so we have negative 2d is equals to, here we can write this as 18 over 4, so we get d is equals to negative 9 over 4. So summarizing the values that we get, we have a is equals to 1/6, b is equals to 1 over 12, c is equals to 1 over 60, d is equals to negative 9 over 4, e is equals to negative 3/4, f is equal to 0, and g is equals to negative 3/4. So we have now our constants, and what we do now is we will substitute this to our equation in our y particular, which we have a while ago. So going back to our yp a while ago, so we have our yp a e to the power of x cubed plus b e to the power of x to the 4th plus c e to the power of x to the 5th plus d cosine x plus e to the x cosine x plus f sine x plus gx sine x. So what we do now is we substitute those values, the values of the constants that we get a while ago here in this equation. So we have yp is equals to, our a is 1 6, so we have e to the power of x cubed over 6 plus our b which is 112, so we have e to the power of x to the 4th over 12. Then c, which is 1 over 60, so we have e to the power of x to the 5th over 60 plus d, which is negative 9/4, so we have minus 9 over 4 cosine x, and for e which is negative 3/4, so we have minus 3/4 x cosine x, and for our f which is 0, so it becomes 0, so we proceed to our g plus g which is 3/4, so we have minus 3/4 x sine x, and that is our y particular. Now since we have y is equals to yc plus yp, so we just add yc here, and we have get yc a while ago, so we have y, and we have our yc is c1 e to the power of x plus c2 x e to the power of x plus c3 x squared e to the power of x, and this is our yc, and adding the yp we have plus e to the power of x cubed over 6 plus e to the power of x to the 4th over 12 plus e to the power of x to the 5th over 60 minus 9 cosine x over 4 minus 3 x cosine x over 4 minus 3 sine x over 4, and this is our final answer. In this problem, we have to show that a can always be determined so that y equals to a x squared e to the power of rx is the solution of the differential equation second derivative of y minus 2r times first derivative of y plus r squared y equals to a erx. So first we have to get the auxiliary equation of this. So and we have to the problem is asking us to solve this using variation of parameters. So first we have to get the auxiliary equation to get the complementary integral. So we have now m squared minus 2rm plus r squared equals to 0. As you can see, we have m minus r squared equals 0. So we have our m1 which is equals to m2 which is equals to r. As you can see, we have distinct roots here. So our complementary equation will be in the form c1 e to the power of rx plus c2 e to the power of rx times x. And from this complementary equation, we can now get our y1, which we will use for our particular integral y1, which is e to the power of rx, and y2, which is x e to the power of rx. And we have the e to the power of rx plus e to the power of 2rx minus x or e to the power of rx, and this will cancel out, so we only have e to the power of 2rx, and this is the value of our w. So now we get our w1, and according to our Wronski to variation parameters, this is equals to setting our y1 to 0 and be having our y2 here, e to the power of rx, then we have our function here a e to the power of rx, and the derivative of this, which is x, or e to the power of rx plus e to the power of rx, and we get here negative ax e to the power of 2rx. And after getting that, we can now get our u1 prime. Our u1 prime is w1 over w. So we have negative ax e to the power of 2rx over e to the power of 2rx. So we have negative ax left. This will cancel out. And then that is our u1 prime. And now getting the w2 for our u2 prime, at our y1 er to the power of rx, setting the y2 to 0, and derivative of this is r e to the power of rx, and writing the function a e to the power of rx, we get a e to the power of 2rx, and our u2 prime is w1 over w, so we have a e to the power of 2rx over our w, which is e to the power of 2rx. So we have our u2 prime, which is equals to a. And getting u1, you have u1 prime is equals to negative ax. To get u1, integrate both sides. So we get our u1, which is equals to negative ax squared over 2. And then getting our u2, we have our u2 prime, which is equals to a. Then integrating this, we get u2 is equals to ax. We have now our u1, which is equals to negative ax squared over 2, and our u2, which is equals to ax, and we have our particular integral, which is equals to y1 plus y1 u1 plus y2 u2. Then substituting the value of u1, u2, and y1 and y2 here, we have our y1, which is e to the power of rx, e to the power of rx times a x squared over 2 negative plus y2, which is x e to the power of rx times ax. simplifying this, we get our yp. We can factor out e to the power of rx, and we get negative ax squared over 2 plus a x squared. And what we get here, we have yp is equals to ax squared to the power of over 2 times e to the power of rx. And since we are given that our y is equals to a x squared e to the power of rx, so from this we can show that a can be determined, so we have to set this to equal. So e x squared e to the power of rx equals a x squared e to the power of rx over 2, and this term here will cancel out, there's no e there, and we can get our a, which is equals to a over 2. And this just shows that a can always be determined. And p of x is equals to x squared. The given differential equation is the Cauchy-Euler equation, which is x squared times second derivative of y plus 2x times the first derivative of y plus the linear density times the square of angular speed times y equals to 0. Then in order to solve this equation, we have to get the solutions of the auxiliary equation. And in getting the auxiliary equation, we have to let y is equals to xm, and we have y prime is equals to mx to the power of minus 1, and our second derivative of y, which is m times m minus 1 times x to the power of m minus 2. After getting this equation, after getting the derivatives, we substitute these derivatives here to the original equation and equating the original equation to 0. So we have here x squared times the second derivative, which is m times m minus 1 x to the power of m minus 2 plus the 2x times the first derivative, which is mx to the power of m minus 1 plus the linear density then squared of angular speed times x to the power of m equals to 0. And here, simplifying this further, we get x to the power of m times m minus 1 plus 2m plus the linear density times the square of the angular speed, which is equals to 0. And getting m, we get m squared plus m plus the linear density times the square of angular speed equals to 0. In this equation, we have to use the quadratic formula. So we get m is equals to -1 plus minus square root of 1 minus 4 rho omega squared over 2. So we get m squared plus m plus the linear density times the square of angular speed equals to 0. In this equation, we have to use the quadratic formula. So we get m is equals to -1 plus minus square root of 1 minus 4 rho omega squared over 2. So we have our m1, which is -1/2 minus 1/2 times square root of 4 rho omega squared minus I, since this is an imaginary number, and for m2 we get -1/2 plus 1/2 square root of 4 rho omega squared minus I. So we have our alpha, which is equals to -1/2, and our beta, which is equals to four rho squared minus I. And we will let lambda will be equals to our 1/2 square root of 4 rho squared minus I. Our lambda here is our parameter that we have created. Then we will let lambda equals 1/2 square root of 4 rho omega squared minus I. Maybe you have wondered why here in our quadratic equation, in our quadratic formula, we have an imaginary number here, since we have assumed that rho omega squared is, since the problem stated that the rho omega squared is greater than 0.25, and since rho omega squared is greater than 0.25, so this term here is always greater than 1. So writing our complementary, so we have this is a homogeneous higher order differential equation. So we have get this equation. So for our y complementary, we have get this equation: y is equals to c1 x to the -1/2 cosine lambda ln x plus c2 x to the -1/2 times sine of lambda ln x. Then after getting that equation, we have to look for the value of our constants, which are the c1 and c2. since we have given that the value of y when x is equals to 1 equals 0, so we have here, we substitute 1 for x, so we have c1 times x to the negative 1 half. 1 to the negative 1 half is 1, so we have c1 cosine lambda times ln of 1 is equals to 0, so cosine 0 plus c2 still times 1 times sine of lambda ln x, which is 0, is equals to 0. So this sine 0 is equals to 0, so we have c1, and this is equals to 1, so we have c1 is equals to 0 equals c2 times x to the power of negative 1 half times sine of lambda ln x. Then we have the condition value of y when x equals to is equals to 0, so substituting e to the value of x to the x, so we have c2x to the negative 1 half sine of lambda, and ln e is equals to 1, so we have only sine of lambda is equals to 0. Then we obtain a trivial solution. Lambda n is equals to n pi, where n is an integer. Using the value of our lambda, which is this, and using this side, we can get the critical angular speed, which is, so we have 1 half then squaring both sides, we get then simplifying this further, we have so getting the critical angular speed, we get 1 half times square root of 4n squared pi squared plus 1 over the linear density. Hence this equation matches to the equation in the problem. And now we have ix is equals to and this is the corresponding solution. Sine and that is how we show that the angular and that is how we show the critical angular speeds and the corresponding deflections that was asked in the problem.